Yeah, well, hello everyone. It's a pleasure to virtually be with you all this morning, evening. I'm going to talk a little bit about what I'm working on with my startup Asteria, which is ultimately building habitats for Mars. I'm going to keep this fairly casual, and yeah, if there's any questions, definitely ping them and I'll try to get to them at the end or afterwards. So briefly, I'm obviously Natalie. I'm a bit of a space nerd, but it wasn't actually always the case. My background was originally in biomedical science, and I went on to do my PhD in neuroscience, looking at using machine learning to predict human decisions. And from there, I went into a role on artificial intelligence strategy with government. And it was actually only during this time that this idea of working on space struck, and it was with this one pivotal moment. I don't know if any of you out there are aware what this is, but back in 2018, SpaceX had their first launch of the Falcon Heavy rocket, and they shot this little starman in a Tesla off into space. He's actually just passed by Mars quite recently. But as somebody who had always been focused on the human side of things, on human health and human, neuroscience, this was the first time that it really dawned on me that within our generation, we had the ability to actually establish human life on the moon, and especially on Mars. And I started to really think, okay, what happens if Elon Musk succeeds and we get to Mars in the coming decade or two? Where are we at in terms of being able to survive this environment? What is it actually like on Mars? So a bit of a fact sheet of what we're looking at once we get there. It's about a third the gravity of what we have on Earth. It's 96% CO2, so we have to generate some oxygen for us. It's about 1% of Earth's atmosphere, so we actually evaporate if we walk outside, which is not great. And temperature is actually not too bad. So it's about -284 to 86 degrees Fahrenheit there. So it's pretty much the balmiest of all the planets that we have available to us. The final kind of difficulty there is that we're also facing this kind of radiation problem. So if we look at a map of these cosmic rays that come in from the universe, the best case scenario we're looking at is about 13 grams per year that are hitting the ground. And what we face on Earth is about 0.6 per year. So we definitely have to take into account how do we protect from radiation, as well as how do we actually create structures which will be very effective at sealing the external environment and creating an indoor environment for us there. And then the last point is really just on the resources that are available to us there. They are fairly limited, but they're available. So we found only within the last few years, really, the first really major evidence that we have water available in the ice caps on the North and South Pole, and we might even have water available in these underground aquifers that we could mine. So we're able to extract water. We're able to maybe in some cases also generate some water, but it's still a very limited supply. And then power, we're probably going to need some level of nuclear power, because we have the ability to set up solar there, but we have dust storms, which prevent us from having solar. So again, power is something which we want to be very precious in our utilization of. The other major thing that we face once we get to Mars is that we are much more isolated there than we are on Earth, or than we even are with our astronauts on the International Space Station. So if you think about somebody that's on the ISS today, you can see them, see them flying overhead overnight. They have all of their major resources like food and water actually shipped into them from Earth. And then if anything actually goes wrong, they have real-time support from everyone that's in mission control, or the greater network of experts. When we get to Mars, our closest support is this little dot in the sky. And I don't know if any of you can see this on your screens. I'll give you a few seconds, but once we get there, Earth is that tiny, tiny little blue dot. It's up to 250 million miles away once we're up there. So we have no real-time communication. And if anything goes wrong, we're waiting for about 2 years until the orbits align and we can actually get resources back from Earth. So ultimately what we actually have to do is to make sure that the habitats there are self-sufficient. So I looked at all of this and I thought to myself, you know, if we send Matt Damon to Mars now, he's actually going to die. So what do we do to make sure that when we send him or when we send ourselves there in the next decade or two, that we ensure that we have survival, not only for, you know, a 2-year trip, but as we start to build a settlement out for much longer periods of time. And with that in mind, I founded Asteria. The goal was to build intelligent habitats that can sustain human life on Mars. And ultimately, if we can sustain life on one planet, it should be possible to sustain that even further beyond eventually. So it's great. That's Mars. I imagine many of you are not focused on building for Mars at the moment. So, you know, what does it have to do with us on Earth? And especially, you know, as a startup, there's not necessarily a massive commercial market for living on Mars right now. So what are the applicable problems that we're facing here? And unfortunately, in many regards, we're actually coming to a position where what we face on Earth is very similar in these first principles to what we face on Mars. And if any of you are aware of the fires that happened in California recently, there's actually this tweet from Brett saying, you know, it's a problem. We're currently making Earth look like Mars faster than we are making Mars look like Earth. And so with our climate change that's happening now, with the warming that is happening, the disruption of the global patterns, not only are we getting to a point where we're being directly impacted with our own health in our environment. So we have air pollution coming into our homes. We have particulate matter when we have things like fires. And then of course we have the risk of death from the fires themselves or from things like hurricanes, which are increasing in their frequency and intensity. So we're actually getting to a point where the role of our houses in protecting us from the external environment is becoming similar to what we face on Mars. On the other side, a lot of what we do with our housing is actually a major contributor towards why we even have the climate crisis at this point in time. I think in the US alone, the carbon emissions from our residential housing are more than the entire of Germany. So if we can actually start to tackle this problem of dealing with limited resources and becoming much more efficient in our resource usage, we help mitigate this process, but we also start to prepare for what it would be like on Mars. And so for us, we really have this universal challenge, which is applicable on both planets. It's how do you create habitation which, one, monitors and ensures an optimal environment for us humans, and that's both in terms of health and also eventually psychology. I think many of us have obviously been in isolation this year and started to realize that being alone inside a home for 24 hours a day is a little bit taxing. When you think about the astronauts that first go to Mars, they're going to have, you know, maybe 5 people with them inside their home. There's going to be no potential to Zoom call anybody on Earth because the communication lag is, you know, 4 to 24 minutes. And so really the only thing that they have there is their home environment and this idea that the home around them is actually protecting them from potential death. And the second part is how do we actually design and operate a house or a habitat with utmost efficiency to make sure that the limited resources we have available are utilized best. So for us, we started with just a prototype design of, you know, what is it actually like to build an autonomous habitat, to build something which can be self-sufficient anywhere we go. And I will mention now we're early stage as a startup. So the first is to build the structure. And for us, we're looking at really building from panelized components. So kind of these Lego blocks that you can integrate with technology, almost like a robot, and build that from a kit of parts and ship this wherever you need. The second is to make sure that the environment is very well monitored with real-time sensors. And here it's kind of crazy because if you're in an automobile or if you're in a plane, you have ridiculous amounts of sensors monitoring everything in your environment. But in the place that we spend 90% of our time, which is indoors, or, you know, since COVID, 100% of our time probably in our homes, we actually have very little idea about what the environmental quality is. We don't track things such as air quality. We don't know if there's mold or moisture in the walls often. And so we take less care of our health in our own environments than we do in somewhere like a car. Third part is to really start to tune the environment to what the occupant needs. And this is one in terms of the personal settings that we have for our climate. So even between a male and a female, there will be differences in what kind of temperature you require. We have different cultural needs as well. And once you go beyond just the climate preferences, you also have the routines and the habits that you have within your home, and how can your home around that start to actually sense this and, you know, even do some of these actions for you. And then finally, we're integrating everything into this kind of central control system. So how do you take this data from your devices, from your sensors, from even, you know, your renewable energy and water systems that we have, integrate this into one place and start to really learn, you know, what are these patterns of activity? Can we predict what's happening in the future? And then can we ultimately use all this to optimize the environment, make sure nothing goes wrong? So where we're at the moment is we've started on the monitoring system. And as I mentioned, we have two major components. The first is the environment and making sure that that's healthy. And the second is the resource system and making sure that that's optimized. So in terms of environment, we have a bunch of sensors running in our little prototype. First is temperature, humidity, lighting, to some extent pressure. This is a bit more important when you have ventilation systems or if you're on Mars. And these are kind of like the homeostatic sensors. So something which has a set range that you're wanting to learn and you're not wanting to either exceed or go below. Then we have air quality, monitoring quite a bit here. So volatile organic compounds, which is often emitted even from the building materials that we've used historically. So your paints or plastics around you. Carbon dioxide, which is kind of this like secret brain killer. It's a lot of the buildings actually today will have this accumulation of carbon dioxide during the day. And there's fairly well-known studies about how this impacts our mental function. So it's something that's important, especially coming from neuroscience, to make sure that we reduce. And then particulate matter, which comes from air pollution or spores or, you know, just general, it's not really any particulate matter that's good for you, dust. And then the final was like motion, which is just, it's more of like a control factor. So can we get to a precision ecosystem in future where it's not only the entire home that has to be, you know, perfectly optimized by this, but it's modulated by where the person spends their time during the day. And in terms of how we keep the environment healthy, it's fairly straightforward. You know, we already kind of have this with Google Nest or Ecobee, your HVAC systems. To read these sensors in and to control the environment is straightforward. To read these sensors in, to learn what the occupants actually really want and what their habits are within that space over the day becomes a bit more complicated. And that's something we're particularly interested in is, can you take, you know, let's call this like Maria, and can you develop a personal profile for what she prefers over the course of the day for temperature, for humidity, even for lighting, and really start to fine tune that environment specifically to her and her ideal states. So the second set of sensors that we have up and running are based around the resources. And here it's really a matter of how do we make sure that we constantly have a very good prediction of the resource horizon or the timeline that we have available with the supplies that we have. We're looking particularly at basically renewable energy systems, and then also like on-site water management and water filtration, and really getting to this point that we can be self-sufficient and be confident in the fact that we're self-sufficient. So things we're monitoring here, again, I think they're fairly straightforward. So we're looking at the solar generation, battery level, energy point usage, which I'll get into. Water level, we consume about 80 to 100 per day. So making sure that we at least have a day there. And then again, water point usage. And I mentioned point usage because if we're really starting to look at a system where, you know, we have no other supplies available, you know, maybe we're not connected to the grid, maybe we're on another planet, maybe we're in a very remote setting, it's no longer really sufficient to be able to kind of like take this like very vague estimates that it's like doing a linear regression model on, you know, we've used, you know, 30 kilowatt hours like this day, we've used, you know, 40 when it was like a super hot day. And so if we look at our patterns of activity over the week and the weather, we can kind of have a vague estimate of what we're going to be doing in future. If it's so extreme that if you run out of energy, you die, or you literally have no energy left, and the same for water, that you've taken this vague estimate of the future and suddenly you find that you actually used much more water than you expected and you had no idea. It's simply not good enough anymore. And so the energy in the water that we're measuring is at a very precise level. So I have, you know, light bulbs that tell me how much energy they're using, which is obviously not very much, but I have like all these like little energy plugs, which will tell me how much every single device in the house is using. Water faucets with flow meters. And so you start to get this very accurate picture of your usage within a household. First thing is, not only does that allow us to create a very good predictive model of the future, but it also starts to get to a point where in future, we also understand what that person's utilization around that house is. And this can help us to start to automate both turning on things, but also turning off things. So can we turn off everything that we know that they're not likely to be using in future? So we save even more energy, save even more water. The other thing that's really important for us is to make sure that if we understand the system very precisely, we can also make sure that there are no faults occurring, or that we at least very rapidly detect any faults that occur. This was actually this is not from a house, this is energy, like voltage systems from the Mars Curiosity rover that we were playing with that data. But you can see here, you can use unsupervised machine learning, and basically like where you see these little spikes is where something has gone wrong in terms of the circuitry. So there was a peak in the voltage there, or you can think about it in a house that, you know, you even had like a leak. So you're suddenly seeing this massive water flow from one particular area of the house, which you're just not expecting. And the red boxes here are being able to basically identify that this is abnormal in that very finite or very precise system. So on Earth, we can make sure that we don't have water leaks. We can make sure that there's not some kind of like crazy fuse break or things like this. But once we get to Mars, we're also making sure that we don't die, basically. I just wanted to quickly mention, so I mentioned we're early stage, we're in the middle of prototyping. I have sensors all around me. And this is the kit that I started out with that I put together, and I've added a bit more since, but if anybody wants to play with this and build your own little home environment, I used a Raspberry Pi with Home Assistant, some ESP8266 chips, and a bunch of sensors. And you can reach out to me on like Twitter, I think maybe best. And I'll send you the list of sensors I used, or help if there's anything you need. So the final thing and more part for software for the house is to really like set up the user interface for people living within the home and kind of turn this into a spaceship. And this is a very rough dashboard that I put together, but really starting to get to this point that it's not just this, you know, kind of like what I think is fairly boring 2D interface, but you're starting to have this like projected display where it's more interactive with you. You have all of your environmental parameters there. You have your events kind of just like on the dashboard, and obviously some personalization starting to happen in that spot. And like really my goal is that we actually get to the point in the future that we have this like pretty badass like Ender's Game style dashboard. I actually reached out to Ash Thorpe, who made this dashboard for the film. I think he thought it was a bit crazy, but we'll get there. So yeah, I've spoken a lot about the software because that's our initial focus, and where we're really targeting business-wise first. But we're also starting to look at what we need in terms of the structure for the housing or the habitats. Obviously, you can have the most advanced thermostat in the world, but if you have poor insulation, if you have gaps, if you've oriented your building incorrectly, then you're still never going to have an efficient building. So something that we've started just like basing our principles off is the passive house structure. So basically, how do you seal a home completely, make it airtight, have, you know, very high grade materials and insulation, and then use only mechanical ventilation to bring that air and moisture, in some cases, into the home. I wasn't necessarily convinced about Passive House to start, and I don't know if anybody has opinions in the crowd, but I thought it was a bit weird to kind of like shut your house off completely. But the more I thought about it, I was like, if you're living in like a place that's like Los Angeles, where you just have pollution all around you, or if you're living on Mars, where you really don't want your external environment to be, you know, coming into your interior settings, then it starts to make sense. And it seems to be crazy efficient. So if you look at the energy rating system, and that one of the systems that we have in at least America, standard home is about 100 on the energy efficiency. You get about, you know, 60 to 80 with Energy Star. And if you're looking at Passive House, this is getting as low as like 15. So it's like very close to a zero energy home. So this is a whole house system that we're starting at least to design with. And then we have finally just like, how do we design these buildings? How do we make systems which can be very readily deployed in remote settings, be very efficient in their construction process, and then one day be also maybe like a lattice bit, like something like super light that could be shipped to another planet and then built there with the available materials. So on Mars, it's this regolith, or the soil that's yeah, it's basically Martian soil that you can kind of like bind and put into structures. And for me personally, I completely hate boxes. I hate squares. I think that they are an incredibly inefficient structure, and you never see them if you look at something which has to be more effective. So, you know, yachts, submarines, planes, any kind of concepts we've ever had for living on another planet with the habitats or spaceships. It's never a box, because it's just, we don't even see these in nature. Because it's not a great structure. So we're really building everything on basis of polygons or triangles, which I think everyone knows is the most fundamental, strong structure that we have available. And also can be combined in lots and lots of different ways to make lots of different triangles. So this is our first like starting design of how do we create a habitat made out of like purely polygons that can be scaled. Ideally, it would be great to have a sphere like a geodesic dome, but I think people maybe are even less inclined to live in circles right now. But yeah, so that's our starting prototype, and that's obviously the habitat in the wild. So yeah, that's just a bit of a run through of where we are at this moment. We're focused really on the software now, building out this sensor and control system to make much more sophisticated and then deploy in a lot of the ultra high efficiency homes that are around. The next step is really getting to this construction phase. You know, like I'm a baby, like, you know, self-trained like architect of only a couple months. So like, I'm always open for criticism or critique on any of the things that we're doing. But next phase is really, how do we create an automated tool, like, you know, fairly computer-driven process for building out a habitat with very high-grade materials in a very like small amount of time, and go from that to being able to deploy it around places on Earth, and then ultimately also start to look at how do we use a similar process, even similar materials to what we have on Mars. So yeah, for us, like we're working with steel because we're not going to be growing trees on Mars for one, but or at least initially. And steel obviously has a lot of great structural properties. And then also looking at things like using rammed earth or natural soil around you, again, because we can start to build this on Earth with a very high local efficiency, but it's also very similar to what we're going to be building with on Mars. Yeah, it's really the future plan. And with that in mind, if anybody here is, interested or looking at things maybe like now or in the coming years, we're definitely hiring software and embedded software engineers very shortly. And then over the course of the next year or two, we'll be looking much more at people that are in architecture and engineering. So I just thought I'd mention that very cheekily. Yeah, thank you everyone for having me, and I hope the rest of the hackathon goes well.